24 millibars. That's the threshold. The number that separates a powerful winter storm from what meteorologists formally classify as a meteorological bomb. A pressure drop of 24 millibars in 24 hours, and a mid-latitude cyclone becomes a detonation. On January 24th, 2025, Storm Éowyn dropped 50 in 10 hours. That's more than double the threshold in half the time. One of the most rapidly deepening windstorms over the European Atlantic in 65 years. A gust of 114 miles per hour erased an 80-year national record on the western coast of Ireland before most of the country had woken up. Category 3 hurricane intensity in January. That's one storm. Now add this. December 24th, 2022. A grid operator serving 65 million Americans entered the worst bomb cyclone in a generation with a 46% reserve margin, more than 3 times the federal minimum. They lost 45,000 megawatts in 48 hours. Rolling blackouts on Christmas Eve. 3 people in Buffalo died because the ambulances couldn't reach them. The roads had stopped existing. And here is what this investigation is actually about. The same atmospheric process driving those events, a warming Arctic destabilizing the polar vortex, warping the jet stream, loading the collision between freezing air and record-warm ocean surfaces with more energy than any prior generation of meteorologists had to account for, is measurably intensifying. The storms are 4 hectopascals deeper now than their historical counterparts, 8 kilometers per hour faster. The infrastructure protecting people from them was calibrated against a baseline that has already shifted. The question is not whether the gap exists. The question is how wide it's getting and who is responsible for closing it. This is that investigation. In 1980, a meteorologist at the Massachusetts Institute of Technology named Frederick Sanders sat down with his graduate student John Giacomo and wrote a paper that would change how the science talked about winter storms forever. The paper was published in the Monthly Weather Review, volume 108. Its title was Dry and Clinical, the way scientific papers tend to be, Synoptic Dynamic Climatology of the Bomb. But the word in that title, the word that would eventually escape the scientific literature and enter the public vocabulary, was not synoptic or climatology. It was bomb. Sanders and Giacomo weren't being dramatic. They were being precise. They defined a specific atmospheric event, an extratropical cyclone, a mid-latitude low-pressure system, the kind that drives the weather systems most of the world's population actually lives inside, whose central pressure drops by at least 24 millibars in 24 hours. That threshold, adjusted by a mathematical formula that accounts for latitude, became the operational definition still in use today. At 60 degrees latitude, the full 24 millibar threshold applies. At the latitude of New York City, the threshold adjusts down to about 17.8 millibars. The underlying physics is the same. What matters is the rate of change, the speed at which the atmosphere reorganizes itself, the speed at which what was a moderate weather system becomes something that kills. What Sanders and Giacomo were drawing attention to in that 1980 paper was not just a naming convention. They were making an argument about intensity and destructive potential. They wanted to draw awareness, as one meteorological encyclopedia would later put it, to the intensity and potential destructive power of the sudden changes resulting from these storms. The word bomb was not chosen carelessly. It was chosen because the pressure drop at the center of these systems resembles in its speed and its consequences a detonation, not a gradual deterioration, not a slow build, a sudden violent transformation of the atmospheric column above a given patch of ocean. Here's the first thing most people don't understand about a bomb cyclone, and it matters for everything that follows. These are not rare events. They occur approximately 40 times per year in the Northern Hemisphere alone. A 2021 study led by Robert Fritzen at Northern Illinois University analyzed North American storms from 1979 to 2019 and found that approximately 7% of all non-tropical low-pressure systems in that period qualified as bomb cyclones. an average of about 18 per year. Just in the North American theater, most of them form over open ocean, which is why most people never experience one directly. The ones that reach populated coastlines tend to become memorable very quickly. And here's the second thing, which is in some ways more important. A bomb cyclone is not, meteorologically speaking, a different category of storm from a hurricane. It is a different machine producing similar outputs. Hurricanes form in tropical and subtropical regions during warm seasons, drawing energy from warm ocean water and the heat released when that water evaporates and rises. Bomb cyclones form in mid-latitudes during cold seasons, drawing energy from the collision between cold continental air masses and warm ocean surfaces, specifically from the baroclinic instability that collision creates. The thermodynamic engines are different. The outputs are not. A bomb cyclone can produce sustained winds of 74 to 95 miles per hour, identical to the first two categories on the Saffir-Simpson scale, the scale used to rank hurricanes. It can produce storm surges. It can produce rainfall rates measured in inches per hour. And in winter, it can do all of that while simultaneously delivering blinding snow and temperatures cold enough to kill an exposed person in minutes. This is what bomb cyclone actually means. Not a heavy snowstorm, not a bad nor'easter, a wintertime hurricane arriving through a completely different mechanism in places that were built for winter, but not for this kind of winter. Consider what 40 times per year actually means. It means that somewhere in the northern hemisphere, right now, there is almost certainly a storm that meets the technical definition of a bomb cyclone, dropping pressure at a rate that Saunders and Giacomo considered alarming enough to name. Most of those storms live their entire violent lives over the open North Pacific or the North Atlantic, where the shipping lanes feel them and the cargo vessels issue distress signals, and the data arrives at research institutions rather than on front pages. The ones that don't stay offshore are the ones this investigation is about, because when a bomb cyclone makes landfall, when the machinery of explosive cyclogenesis arrives over a populated coast rather than an empty stretch of ocean, the consequences it produces are not proportional to anything in most people's prior experience of winter weather. The Saffir-Simpson comparison is worth dwelling on. The scale was developed in the early 1970s by civil engineer Herbert Saffer and meteorologist Robert Simpson, specifically to communicate to the public and to emergency managers the destructive potential of approaching tropical cyclones. Category 1 begins at 74 miles per hour sustained wind. Category 2 extends to 95. Both categories are associated with significant structural damage, widespread power outages, and dangerous debris fields in populated areas. Both have historically prompted mandatory evacuations of coastal zones. A bomb cyclone operating in the 74 to 95 mile per hour range is, by the only metric that matters for what it does to buildings and people and infrastructure, a Category 1 to Category 2 hurricane. It simply arrived through a different atmospheric mechanism and doesn't appear on the Hurricane Center's advisory products. That distinction matters enormously to the warning architecture. It matters not at all to the house whose roof comes off. The question this investigation is going to pursue across the next 2 hours is not whether these storms are dangerous. That's documented in numbers you'll find hard to set aside. The question is whether the systems we've built to protect people from them are calibrated for the storms that are now arriving, or whether they were calibrated for the storms of 50 years ago when Frederick Sanders was first putting a name to what he was seeing. Because there's a growing body of evidence, observable in the data and in the institutional records, that the gap between what these storms can do and what our preparedness frameworks expect them to do is not narrowing. It is widening, and the mechanism driving that widening is not, it turns out, located anywhere near the storms themselves. It is located at the top of the world. But before we get to the mechanism, we need to understand the machine. Because the way a bomb cyclone works is genuinely strange. Stranger than most weather coverage conveys. And you can't fully appreciate what's changed about these storms without first understanding what they have always been. The atmosphere over the North Atlantic Ocean in December is not calm. It is a zone of perpetual contest between two air masses that have almost nothing in common with each other. On one side, the cold, dry, dense air that is poured off the North American continent, air that has spent weeks over the frozen interior of Canada and the Arctic, air that carries temperatures measured in the negative 10s and negative 20s of degrees Fahrenheit. On the other side, the warm, moist, unstable air that sits above the Gulf Stream, the ocean current that carries tropical heat northward along the American coastline at speeds of up to 5 miles per hour, pouring roughly 30 million cubic meters of water per second through the Atlantic basin, keeping sea surface temperatures in that region dramatically warmer than they should be at that latitude. Where those two air masses meet is called a baroclinic zone, and in a baroclinic zone, the atmosphere is unstable in a specific measurable way. Because cold air is denser than warm air, the two masses don't sit cleanly side by side, they tilt. The boundary between them slopes upward from the surface, and that sloping boundary is a ramp that the atmosphere can run down, releasing potential energy, spinning up circulation. This is baroclinic instability. It's the same fundamental process that drives most of the mid-latitude weather that actually affects human populations. But under the right conditions that occur roughly 18 times a year in the North American theater alone, the instability doesn't just generate a weather system, it generates a detonation. The right conditions require several simultaneous ingredients. The temperature contrast across the baroclinic zone needs to be sharp. The sharper the contrast, the more potential energy available for release. The upper level jet stream, the narrow band of fast-moving air in the upper troposphere, roughly 6 to 9 miles above the surface, needs to be positioned in a way that supports divergence aloft. When the jet stream diverges above a surface low-pressure system, it removes atmospheric mass from the column overhead. Less mass overhead means less pressure at the surface. Less pressure at the surface means the load deepens. And as the load deepens, the pressure gradient between its center and its surroundings steepens, which means winds increase, which means more moisture and heat flux is pulled off the ocean surface, which releases more latent heat into the atmosphere, which provides more energy to the deepening system. This is the feedback loop at the center of explosive cyclogenesis. Each step reinforces the next. The researchers who studied one super explosive cyclone over the Gulf Stream found that the diabatic heating, the latent heat released when water vapor condenses as the storm draws moisture off the ocean, was the single largest contributor to the storm's explosive development, outweighing even the baroclinic vorticity effects. Once the loop engages, the storm can deepen faster than any model calibrated to past events would predict. This is why meteorologists, when they see the conditions aligning for explosive cyclogenesis, describe their alarm in terms that don't usually appear in scientific writing. The atmosphere is about to do something fast. The Gulf Stream is where most North Atlantic bomb cyclones find their fuel. The Kuroshio Current, the Pacific equivalent flowing northward along the coast of Japan, does the same job for North Pacific bomb cyclones. Sanders and Giacomo identified both of these warm ocean currents as the primary geographic locations for maximum explosive cyclogenesis frequency back in 1980, and the 40-plus years of data collected since have confirmed their analysis. These two narrow zones of anomalously warm ocean water sitting in the path of cold continental air outflows are the geological features that make bomb cyclones possible at the scale and frequency at which they occur. But here's what has changed since 1980 and what makes the warm ocean fuel factor more significant now than it was then. The sea surfaces along both the North Atlantic and North Pacific have been warming. North Atlantic temperatures in 2023 and 2024 reached record-breaking levels that Climate Central described as near record again heading into 2025. Warmer ocean surfaces mean more moisture available for evaporation. More moisture means more latent heat available for release when that moisture condenses inside a developing storm. More latent heat means faster deepening during explosive cyclogenesis. The fuel tank is larger than it used to be, and the storms are drawing on it. the minimum central pressure achieved by the 1993 storm of the century, the benchmark event we'll examine in detail later in this investigation, was 960 millibars. For reference, normal sea level pressure is approximately 1,013 millibars. The 960 millibar reading recorded during the 1993 storm is comparable to the central pressure of a strong tropical storm approaching hurricane intensity. That number, 960, was treated at the time as extraordinary. It still is, but as we'll see when we examine the events of 2022 and 2025, it is no longer the outer edge of what the atmosphere has shown it is capable of producing over the mid-latitude oceans. The engine room of a bomb cyclone is the collision zone between old air and warm water. What's changed is the temperature of the water. And that change, modest in absolute terms, has consequences in the storm's output that are anything but modest. The specific thermodynamics are worth tracing precisely because they explain something important about why small changes in ocean temperature produce disproportionate changes in storm intensity. The Clausius-Clapeyron relation, one of the foundational equations of atmospheric thermodynamics, tells us that for every degree Celsius of warming in the lower atmosphere, the atmosphere can hold approximately 7% more water vapor. More water vapor means more moisture available for evaporation from the ocean surface into the developing storm. More moisture means more condensation as that water vapor rises and cools. More condensation means more latent heat released into the atmospheric column, the diabatic heating that the frontiers in earth science analysis identified as the dominant contributor to super-explosive cyclogenesis events. The feedback is not linear. A small increase in ocean surface temperature translates, through this chain of physical relationships, into a significant increase in the latent heat available to a developing storm. The Gulf Stream is running warmer than historical records support. The North Atlantic Sea surface temperature anomalies that Climate Central tracked through 2023 and 2024, anomalies that reached record-breaking levels, are not a temporary fluctuation. They reflect a decades-long trend in ocean heat content that is reshaping the fuel environment for every North Atlantic bomb cyclone that forms over the western half of the basin. When Saunders and Giacom were collecting data for their 1980 paper, the ocean was cooler. The storms they analyzed were drawing on a different fuel reservoir than the ones arriving now. The definition they created has not changed. The environment producing the events that definition describes has changed considerably. December 21st, 2022, a low-pressure system begins forming over the northern plains, Montana, North Dakota, South Dakota, Wyoming. In its early stages, it's unremarkable enough that some forecast models aren't treating it with particular alarm, but the conditions around it are already being watched. The jet stream is positioned to provide upper-level support. The temperature contrast between the Arctic air mass that has settled over the continental interior and the warmer air to the south and east is sharp. The Weather Channel's meteorologists, reviewing the model output, predict it will turn into a bomb cyclone. They're right. Over the next 48 hours, the system deepens and moves. By December 23rd, it's hammering the Great Lakes region with winds that, in a different season, would trigger hurricane warnings. Duluth, Minnesota, records gusts of 74 miles per hour. Grand Marais Harbor, up the shore of Lake Superior, hits 82. These are Category 1 hurricane wind speeds. In December, in the interior of North America, the National Weather Service, reviewing the storm's documentation, would later call it one of the greatest extents of winter weather warnings and advisories the agency had ever recorded. Then comes the pivotal 12 hours. As the storm sweeps from Indiana into Ontario, between the afternoons of December the 23rd and 24th, its central pressure plummets 35 millibars. The bomb cyclone threshold is 25 millibars in 24 hours. Elliott exceeds it by 40% in roughly half that time. The pressure gradient steepens. The wind field expands. The Arctic air that the storm is drawing southward carries wind chills in the northern plains of -70 degrees Fahrenheit. The National Weather Service's official characterization of what arrives next is careful in its language, as institutional meteorological communications tend to be. One in a generation storm. That is the phrase they use. It is accurate, and it is also, as we'll come to understand, a phrase that will need to be revised. Buffalo, New York sits at the eastern end of Lake Erie. In most winters, it receives more snow than almost any other American city its size because it sits directly in the path of the lake effect snow machine. Cold air crossing the still unfrozen lake, picking up moisture, depositing it as snow on the lee shore. But what arrives in Buffalo during the late hours of December 23rd is not lake effect snow in any familiar sense. It's a bomb cyclone at peak intensity, arriving simultaneously with a lake effect event, the two systems merging into something the city's historical records have no exact parallel for. What follows is 37.5 consecutive hours of blizzard conditions. That number, 37.5, is not a rounding. It is the documented duration of conditions meeting the National Weather Service's technical definition of a blizzard. Visibility below a quarter mile and winds above 40 miles per hour. Sustained, without interruption. It is the longest blizzard in Buffalo's recorded history. The peak gust in the city reaches 79 miles per hour. The lake effect component deposits snow at rates that, at their peak, exceed 2 inches per hour. Rates at which roads become impassable within 30 minutes of being plowed. The total lake effect accumulation over the 5-day event exceeds 56 inches. That's nearly 5 feet of snow, on top of hurricane-force winds, on top of wind chills that make exposed skin a medical emergency within minutes. On December 24th, Christmas Eve, 110 million Americans across 36 states are under wind chill alerts. That's roughly a third of the country's population. The National Weather Service describes the scope as one of the greatest extents of winter weather warnings and advisories in the agency's history. The storm is simultaneously producing blizzard conditions across the Great Lakes, sub-zero temperatures across the plains, freezing rain along the mid-Atlantic coast, and gusts that knock out power from Maine to the Pacific Northwest. Grand Rapids, Michigan, experiences blizzard conditions, zero visibility, from 10 in the morning to 10 at night on December the 23rd, then reduced visibility continuing until 5 in the afternoon on December 24th. The city receives 24.8 inches of snow over 4 days. Baraga, in the Upper Peninsula of Michigan, receives 42.8 inches from lake effect enhancement. Buffalo Niagara International Airport shuts down completely. It stays shut for 5 days. More than 18,200 flights are canceled across the country between December 22nd and 28th, one of the largest single-event flight disruption totals in aviation history. And then the deaths. Erie County Executive Mark Poloncarz holds press conferences over the following days to account for them. 41 deaths confirmed in the Buffalo area alone. Some found dead inside their vehicles. Some found dead in the open. Deaths from cardiac arrest while shoveling snow. At least one from carbon monoxide poisoning. And three specific documented deaths, attributed not to the storm's direct physical violence, but to delayed emergency medical response. Ambulances that couldn't reach patients. Fire trucks that couldn't navigate roads buried under drifting snow. The storm didn't just kill people directly, it disabled the systems meant to prevent people from dying of other causes while the storm was happening. By the final count, Winter Storm Elliott kills at least 100 people. But the number that will follow this storm into policy debates for years, the number that reveals the gap between what the systems protecting people are designed to handle and what they actually faced, is not the death toll. It's the grid number, and that number is 45,000. Before we get to that number, it's worth sitting with the full scope of what Elliott produced in the 72 hours when it was at its most violent. Because the death toll and the operational failures are the outcomes. But the atmosphere was doing something that people who weren't inside it may struggle to viscerally understand. Imagine standing in Buffalo on the morning of December 24th, wind chills at negative 40 degrees Fahrenheit. Visibility 0, not reduced, not impaired, 0. The snow is not falling so much as moving horizontally at 70 miles per hour, driven by winds that have been sustained above blizzard threshold for more than 30 consecutive hours. A car that stops for any reason, a traffic sign, a stalled vehicle ahead, a momentary uncertainty about whether the road still exists, can be buried to its windows within 30 minutes. Emergency responders dispatched to a call may arrive to find their vehicle immobilized before they reach the patient. The patient, sheltered and waiting, is unreachable. This is not a failure of emergency services personnel. It is a failure of the physical conditions under which those services are expected to operate. Conditions that the planning framework described as manageable under a once-in-a-generation worst case. The SAISH that Elliott generated in Lake Erie is worth noting as a compound effect that rarely receives coverage. The storm's sustained west to east winds over the lake created a SEISH, a standing wave oscillation in an enclosed body of water caused by sustained wind, that produced record low water levels in the western basin of the lake, pulling water toward the eastern end. That shift added to the flooding and ice conditions along the Lake Erie shoreline and contributed to dangerous surf conditions that persisted after the wind field had already begun to weaken. A storm strong enough to measurably displace the water level of one of the Great Lakes is operating at a scale that transcends most people's intuitive model of winter weather. It is not a bad snowstorm. It is a geophysical event. PJM Interconnection is the grid operator for one of the largest regional transmission organizations in the world, serving 65 million people across 13 states and the District of Columbia, from Illinois to New Jersey, from Michigan to Tennessee. It's not a utility company in the household sense. It coordinates the bulk power market, manages the transmission grid, and ensures that at any given moment, the generation capacity available in its service area exceeds the demand being placed on it by a sufficient margin that the system stays stable. In November of 2022, 1 month before Winter Storm Elliott, NERC, the North American Electric Reliability Corporation, the federal body responsible for monitoring grid reliability, released its winter assessment. The assessment warned that Texas, the Midwest, and New England were at risk of supply shortfalls in an unusually severe storm. PJM, whose service area covers the Mid-Atlantic and much of the industrial Midwest, was assessed differently. PJM entered the winter with what its own figures showed as 184,400 megawatts of available generation capacity against a projected peak demand of 126,400 megawatts. That's a reserve margin of 46%, more than 3 times larger than NERC's minimum reliability target. On paper, PJM had enough cushion to absorb a significant unexpected shortfall and still keep the lights on. On December 23rd and 24th, the cold knocked out 45,000 megawatts of that capacity. That figure comes from PJM spokesperson Jeff Shields, who reported it to E&E News in the days following the storm. 45,000 megawatts of generation capacity that failed to start when called upon, or tripped offline while running. A combination of plant failures, unavailable fuel, and operational cutbacks. Shields noted that the full breakdown of causes wasn't yet available, but the scale was not in dispute. A grid system that had entered the storm with a 46% reserve margin, more than 3 times the minimum target, lost 35% of its available generation within 48 hours of the storm's peak intensity. On Christmas Eve, more than 1.6 million American customers were without power. The Tennessee Valley Authority, which serves parts of Tennessee, Alabama, Mississippi, Georgia, Kentucky, North Carolina, and Virginia, was among the operators that turned to rolling blackouts on December the 23rd and 24th. That action, formerly known as the Electric Load Curtailment Program, or ELCP, had never been invoked before. It was the first time in the TVA's history that it had been necessary to order local power companies to reduce their load in rotating increments to prevent a wider grid collapse. The Oak Ridge National Laboratory's subsequent analysis of the event described how a predicted storm, one that was in the forecast, one that the system had been warned about, produced unanticipated challenges for power management organizations and utility companies that no prior planning exercise had fully captured. The Federal Energy Regulatory Commission and NERC launched a joint investigation in January 2023. What that investigation and subsequent analysis revealed was something that Arshad Mansour, the CEO of the Electric Power Research Institute, stated publicly with unusual directness. We clearly are seeing the effects of the warming of the planet. Our planning process does not take that into account. Mansour's statement is worth sitting with at length because it comes from an unusual source. The Electric Power Research Institute is not an environmental advocacy organization. It is the research arm of the electric utility industry, funded by the utilities themselves, providing technical analysis that shapes the planning and investment decisions of the companies that operate the American power grid. When the CEO of that organization says publicly that the planning process does not account for the observable effects of a warming climate on extreme weather, he is not making a political statement. He is making a technical assessment about the gap between his industry's planning methodology and the atmospheric data. And that assessment was made in the context of a storm where the gap had just been measured in 45,000 megawatts of lost generation capacity on Christmas Eve. The industrial risk consultant's analysis, cited in E&E News, examined the proposed cold weather reliability standard that was being developed for Louisville, Kentucky, part of the PJM service area, at the time of the investigation. The proposal was to require generation facilities to remain operational at a minimum temperature of 4 degrees Fahrenheit. That number was derived from historical weather records, from what the coldest temperatures on record had been in that location over the preceding decades. It was a backward-looking standard, and between December 22nd and 23rd, 2022, the actual recorded low temperature in Louisville plunged from 43 degrees Fahrenheit to -6, not 4 degrees, -6, a gap of 49 degrees between the regulatory planning assumption and what the atmosphere had already delivered. The question that Gordon Van Wheely, the CEO of ISO New England, another major grid operator, asked at a FERC-sponsored conference in September of 2022, months before Elliott even formed, now hangs over all of this. There are limits to what FERC and state regulators can do under their respective jurisdictions. I have really been struggling with who is responsible for mitigating the impact of these risks. Is it the federal or the state regulator? His question was not answered before Elliott arrived. It was not fully answered in the investigation that followed. And the reason it matters is that the storm that exceeded PJM's planning assumptions by 49 degrees in Louisville was not the extreme event in this investigation. It was the baseline. The ORNL report that followed the Elliott grid failures contains a detail that is easy to overlook, but speaks directly to the systemic nature of what happened. The Tennessee Valley Authority's electric load curtailment program, invoked for the first time in TVA history during Elliott, requires local power companies to receive and act on load reduction orders from TVA. The communication protocol for those orders assumes that the parties receiving them have functional communication infrastructure, adequate staffing, and time to implement the reductions in an orderly fashion. During the peak of Elliott, the Step 50 request, the first request for a 5% load reduction, was followed almost immediately by escalating steps requiring deeper and faster cuts. The ORNL analysis described the quick succession of steps and extra calls and texts as creating coordination challenges the communication systems weren't designed for. This is the institutional equivalent of the thundersnow problem we'll examine later in this investigation. The standard design handles normal sequences. It is not stress tested against the scenario where the entire event unfolds faster and more intensely than the design parameters anticipated. The TVA's protocol worked adequately when load curtailment was a theoretical possibility. When it became a live emergency requiring real-time coordination across a system stressed by the same storm that was driving the demand for curtailment, the protocol revealed its limits. The ORNL recommendation following the analysis was essentially to redesign the communication architecture for the reality of simultaneous multi-system stress, a significant undertaking that had not been completed by the time the next major winter storm arrived, because 13 months after Elliott, on the other side of the Atlantic, the atmosphere produced something that made Elliott look, in strictly meteorological terms, like a prologue. On January 21st, 2025, the UK Met Office named the fifth storm of the 2024 to 2025 European windstorm season. The name came from a list based on public suggestions. It was taken from J.R.R. Tolkien's novel, The Lord of the Rings, Éowyn, pronounced A-Y-O-Wyn. It was, at the time of naming, a rapidly intensifying low-pressure system tracking across the North Atlantic. What the meteorologists watching it already understood was that it was drawing energy from two sources simultaneously: the record warm North Atlantic sea surface temperatures that had persisted from 2023 into 2025, and jet stream energy that had, just days earlier, helped produce historic snowfall on the U.S. Gulf Coast. The same atmospheric disturbance that buried parts of the American South under snow was now reorganized and amplified by the Atlantic, heading for Ireland and the United Kingdom. Met Éowyn, the Republic of Ireland's National Meteorological Service, issued an orange wind warning for all 26 counties on January 22nd. By January 23rd, that warning had been upgraded to red, the highest level, reserved for conditions that are extremely destructive and dangerous to life. Cathal Nolan of Ireland's Weather Channel, watching the model output converge on a scenario that the country's historical records had no parallel for, described what was coming as a generational storm. He meant that in the precise sense, a storm that arrives once in a person's lifetime and leaves marks that persist in the institutional memory for decades. The oceanographic buoys deployed by Met Éowyn in the North Atlantic, tracking the storm as it approached, recorded the pressure drop. The central pressure of Éowyn fell approximately 49 millibars in 10 hours. 24 hours total pressure drop, approximately 50 millibars. The bomb cyclone threshold is 24 millibars in 24 hours. Éowyn exceeded it by more than double, one of the most rapidly deepening European windstorms recorded in 65 years. The minimum central pressure reached 939 millibars, one of the lowest pressure readings associated with a storm making landfall on Ireland and the United Kingdom in more than 6 decades. At approximately 5 in the morning, GMT on January 24th, at the Macehead Atmospheric Research Station on the western coast of Ireland in Connemara, County Galway, the anemometers recorded a wind gust of 114 miles per hour. At the same station, at approximately 4 in the morning, the sustained wind speed reached 84 miles per hour. To put those numbers in context, Category 1 hurricane threshold is 74 miles per hour sustained. Category 3 begins at 111 miles per hour. The gust at Macehead on the morning of January 24th was Category 3 intensity on the island of Ireland in January. The previous record for a wind gust anywhere on the island of Ireland had been 113 miles per hour, measured at Foynes in County Limerick in 1945. The record had stood for 80 years. Éowyn erased it in a single morning. At Cairnwell in Scotland, gusts reached approximately 135 miles per hour. At Drumalbene, Scotland, 100 miles per hour. At Magilligan, Northern Ireland, the pressure reading dropped to 948 millibars, a new record low for the month of January in Northern Ireland, and the lowest pressure reading at that location since records began in at least 1900. UK Met Office Chief Meteorologist Jason Kelly issued an advisory that morning. There is potential for gusts of 100 miles per hour in exposed locations within the red warning area. Over 715,000 homes, farms, and businesses across the Republic of Ireland lost power at the peak of the storm. Close to 30% of the nation's total electricity customers. Nearly 100,000 more in Northern Ireland. 20,000 in Scotland. In Dublin, a skating rink's roof structure failed under the wind load and collapsed. In County Donegal, a man died when a tree fell on his car. In Helensburgh, Scotland, a swimming pool roof was destroyed. Wind turbines, the irony is not small, were toppled by wind speeds that exceeded their operational tolerances. Haley Fowler, a professor of climate change impacts at Newcastle University, watching the data come in, offered an assessment that was neither alarmist nor dismissive. As the climate gets warmer, we can expect these storms to become even more intense, with greater damages. She said it as a scientific statement. The data behind it was at that moment still being pulled off instruments that the storm had partially destroyed. 10 days after Éowyn made landfall, on February 2, 2025, approximately 39,000 Irish customers were still without electricity. ESB Networks, the government-run body managing Ireland's electrical grid, had requested and received assistance from 7 other European nations. Engineers from Austria, Finland, France, Great Britain, Germany, the Netherlands, and Norway, all working to restore a power grid that a single storm had partially dismantled. The EU Civil Protection Mechanism was formally activated. Ireland had asked for emergency help from the European Union to manage the aftermath of a winter weather event. That is not a routine outcome. The 10-day restoration timeline deserves specific attention because it illustrates the second-order consequences of infrastructure that is calibrated for storms that fall within historical parameters. ESB Networks was working to restore power to 39,000 customers who were still without electricity a full 10 days after the storm made landfall. For context, a typical major storm in Ireland might knock out power to tens of thousands and restore most of it within 48 to 72 hours. 10 days of sustained outage for tens of thousands of customers in January, in temperatures consistently below 10 degrees Celsius, represents a qualitatively different category of grid stress. The infrastructure had not been designed to absorb and recover from an event that deposited substantially more energy into the wind field than the standard design storm. The Galway Aquarium flooded in the storm surge. Instrumented boulders installed by a team of Notre Dame scientists on the Aran Islands, deployed specifically to measure the wave transport physics during large Atlantic storms, received what researcher Andrew Kennedy described as a big mover event, the kind of wave-driven movement that reshapes coastlines. Wind turbines were toppled. A 100-year-old building in Hale, Manchester, collapsed. A Dublin ice skating rink, a steel-framed structure built to modern engineering standards, failed structurally before the storm had reached its peak intensity at that location. These are not the failures of antiquated infrastructure. These are the failures of infrastructure designed against a historical wind load distribution that Éowyn exceeded by a margin sufficient to reveal the inadequacy of the design baseline. The jet stream energy that powered Éowyn's extraordinary deepening traced back, meteorologically, to the blizzard that had buried the U.S. Gulf Coast in snow just days earlier. The same atmospheric disturbance that produced historic snowfall in Louisiana and Texas reorganized over the Atlantic and arrived in Ireland as a record-breaking bomb cyclone. The storm system was not contained. It was a hemisphere-scale event that happened to deliver its most catastrophic phase on the western edge of Europe, erasing 80-year records before moving on to Norway. The global atmosphere does not observe national boundaries or institutional jurisdictions. And Éowyn had a feature that Elliott didn't, a feature that tells you something specific and important about the atmospheric conditions that allowed its pressure to drop more than double the bomb cyclone threshold. It's called a sting jet. And to understand why it matters, we need to go inside the structure of a mature bomb cyclone, into the specific geometry of the storm that creates conditions for atmospheric violence that most forecast models still struggle to fully capture. That's where we're going next. Imagine you are watching a satellite loop of a mature extratropical cyclone over the North Atlantic. What you see looks nothing like a hurricane. There's no eye, there's no symmetric spiral of organized cloud bands reaching out from a calm center. What you see instead looks like a vast comma, the kind of comma you'd find in a sentence, but rendered in cloud, stretched across thousands of miles of ocean. The hook of the comma is called the comma head. The tail extends southward and westward along the cold front. And this shape, which meteorologists can identify from space and track across hemispheres, is not decorative. It is the map of a machine that is at its peak, transferring energy from the ocean surface to the atmosphere at a rate that has no peacetime equivalent. The comma structure reflects the 3 distinct air streams that are circulating inside a mature extratropical cyclone at the same time, each with its own origin, its own temperature, and its own role in the dynamics of the system. The warm conveyor belt is the broad, ascending flow of warm, moist air ahead of the cold front, air that rises from near the surface to the upper troposphere, cooling and condensing as it climbs, forming the widespread cloud shield, and precipitation that most people experience as the leading edge of a major winter storm. The cold conveyor belt is the lower level flow of cold air wrapping around the back of the system, moving toward the center of the low and then rising into the comma head, the source of the heaviest snowfall for areas north and west of the storm center. And then there is the dry intrusion. The dry intrusion is the third airstream, and it is the one that matters most for understanding how a bomb cyclone can deliver wind speeds that exceed even an experienced meteorologist's expectation. It is a tongue of dry, cold air descending from the upper troposphere, sometimes from the stratosphere itself, curving down behind the cold front and wrapping around the back of the low-pressure system. In most extratropical cyclones, the dry intrusion stays elevated. It sweeps around the upper portion of the comma head and curves back out without reaching the surface. But under specific conditions that aligned during Storm Éowyn in January 2025, the dry intrusion descends all the way to the surface. And as it descends, it accelerates. This is the sting jet. The term was coined in the 1990s by researchers studying the dynamics of intense North Atlantic cyclones. It describes a narrow area of exceptionally strong winds, 100 miles per hour or faster, that are drawn down from the mid-troposphere to the Earth's surface, concentrated in the hook at the tip of the comma head. The sting jet is narrow. It can be as little as 20 to 30 miles wide. It lasts for only a few hours at any given location, and it is frequently not captured by standard operational forecast models, which lack the spatial resolution to resolve a wind maximum that narrow. This is not a minor technical limitation. It means that the most violent phase of an intense bomb cyclone can arrive with less warning than the storm's official forecast implies, in a corridor narrower than most emergency planning scenarios account for. During Éowyn, the sting jet was confirmed by meteorologists as the mechanism behind the record measurements at Mace Head and the extraordinary gusts recorded across Western Ireland and Scotland. The pressure drop that brought Éowyn to 939 millibars provided the upper-level divergence that powered the dry intrusion. The record-warm Atlantic sea surface temperatures provided the latent heat that accelerated the storm's deepening. And the sting jet, the specific feature that no standard forecast model reliably captures, delivered winds at the surface that exceeded the forecast upper bound and erased an 80-year national record before most of the affected population had fully woken up. At Cairnwell, in the Scottish Highlands, approximately 135 miles per hour. That is Category 2 hurricane intensity on the Saffir-Simpson scale, not over the open ocean. In the Scottish Highlands, at 5 in the morning on the 24th of January, the Mace Head Atmospheric Research Station's anemometer, mounted at 40 meters above ground level, recorded sustained winds of 84 miles per hour at approximately 4 in the morning, then a gust of 114 miles per hour within the following hour. The instrument's data briefly interrupted as the wind intensity exceeded the sensor's reliable operating range. The storm was, in the most literal sense, breaking the measuring equipment. The sting jet tells us something specific that is worth pausing on. It tells us that the most dangerous moments in an intense bomb cyclone are the moments that are least well represented in the forecast. The standard warning said gusts of up to 100 miles per hour in the red warning area. That was accurate as a description of what the model could see. What the model could not see was the sting jet's corridor delivering 135 miles per hour in the Highlands and collapsing structures in Ireland that had stood for a century. There is a fundamental asymmetry between the precision of the atmospheric event and the precision of the forecast describing it. And that asymmetry matters more as the storms intensify, because a sting jet at the tail of a cyclone that is deepened 50 millibars is not the same animal as a sting jet on a cyclone that deepened 24 millibars. Scale changes the output non-linearly, but the sting jet is a symptom. To understand why Éowyn could reach a pressure drop more than double the bomb cyclone threshold, to understand why Elliott's 35 millibar drop in 24 hours was itself 40% above threshold, you need to go somewhere that seems at first entirely unrelated to winter storms on the North Atlantic. You need to go to the Arctic, because the mechanism driving the escalation of these events is located there, and it is stranger than most coverage of extreme weather describes. The sting jet's history as a concept is itself worth a brief note because it explains why the forecasting gap persists. The phenomenon was identified and named by researchers in the late 1990s and early 2000s, studying archival data from intense North Atlantic cyclones. One of the storms that contributed most to its identification was the Great Storm of 1987. The devastating windstorm that struck southern England and northern France in October of that year, killing 22 people and felling 15 million trees. The British Met Office famously did not forecast the storm's full severity, and a meteorologist's now infamous statement to a television viewer who had asked about a rumored hurricane, "Don't worry, there isn't one," became a symbol of forecast failure. What the post-event analysis eventually revealed was that a sting jet had been responsible for the worst wind damage. The models of 1987 couldn't see it. The models of 2025 still struggled to resolve it with operational reliability. The sting jet has been known to science for decades. It remains a systematic blind spot in the forecast, and the storms in which it most commonly appears are precisely the storms that are intensifying most rapidly under the atmospheric conditions the Arctic amplification mechanism is producing. The Arctic is warming. That statement has been in scientific and public discourse long enough that it may have lost some of its force. So let's be specific about what it means in the context of this investigation. The Arctic is warming approximately 2 to 3 times faster than the global average, not slightly faster, 2 to 3 times. That asymmetric warming, polar amplification, in the technical literature is not a future projection. It is an observable measurement. It is in the reanalysis data sets that go back to the mid-20th century, and it is producing a consequence that is, on first encounter, deeply counterintuitive. A warming Arctic is making winter more violent at mid-latitudes. To understand why, you need to understand what drives the polar jet stream. The jet stream is a narrow band of fast-moving air in the upper troposphere, roughly 6 to 9 miles above the surface, that meanders around the hemisphere in a roughly west to east direction. Its speed, the speed of the winds within it, which can exceed 200 miles per hour in its core, is powered by the temperature difference between the Arctic air mass and the warmer mid-latitude air mass to the south. A large temperature difference means a strong temperature gradient. A strong temperature gradient, through the physics of thermal wind balance, means faster jet stream winds. A fast jet stream tends to stay relatively circular, keeping cold Arctic air penned up in the polar region where it belongs. Here is the paradox. As the Arctic warms 2 to 3 times faster than the mid-latitudes, the temperature difference between Arctic air and mid-latitude air decreases. A smaller temperature difference means a weaker temperature gradient. A weaker gradient means a slower, more meandering jet stream, one that develops larger waves in its path, waves that can amplify into deep troughs and ridges that persist for days or weeks. A jet stream with deep, persistent waves allows cold Arctic air to push farther southward, sometimes dramatically farther, and warm, mid-latitude air to surge farther northward. The cold outbreaks that result are more extreme than they would be in a world where the jet stream was stronger and more circular. Graham Madge, a spokesperson for the UK Met Office, described the mechanism in direct terms. When it gets to our level, it can cause disruption to the flow of the jet stream. The jet stream in a normal state is what drives our weather, and it is these interruptions to the jet stream which bring us different weather patterns. And Jason Furtado, a meteorologist at the University of Oklahoma, made the specific connection to bomb cyclones explicit. When the circulation around the polar vortex becomes less and less circular in shape, the cold air normally confined to the Arctic can expand southward to the mid-latitudes, including the US, Europe, and East Asia. This southward expansion of Arctic air doesn't just produce cold outbreaks. When that Arctic air collides with the warmer air over the Gulf Stream or the warm ocean surfaces along the east coast, the temperature contrast, the baroclinicity that drives explosive cyclogenesis, becomes sharper than it would otherwise be. The Arctic amplification mechanism is, in effect, loading the collision zones with more energy. It is simultaneously making the cold air colder and more available at mid-latitudes and making the ocean surfaces warmer. The two ends of the baroclinic contrast are both being amplified by the same global warming signal through different mechanisms, with the result that the conditions for explosive cyclogenesis are more intense than they were when Frederick Saunders was first describing the phenomenon. The peer-reviewed evidence for this intensification now spans decades of observational data. A study published in Communications, Earth, and Environment, a Nature journal, in October of 2023 analyzed multiple reanalysis datasets covering the period from the 1950s through the 21st century. Its conclusion, the results indicate an intensification of Arctic cyclone activity over the last 7 decades. There has been a long-term shift of the maximum cyclone counts from weaker to stronger cyclones, and a pronounced lengthening of the duration of strong cyclones. The mechanism driving this intensification in the analysis was enhanced lower troposphere baroclinicity, amplified winter jet stream waves over the subpolar North Atlantic. That is the observational record, not a model projection, not a worst-case scenario. The last 7 decades of data showing a shift in the distribution of cyclone intensity, fewer weak events, more strong ones, and the strong ones lasting longer. The Climameter research team, led by David Faranda at the Institut Pierre-Simon Laplace in France, performed a specific attribution analysis of Storm Éowyn. They compared current-era storms, 1987 to 2023, with equivalent storms from the earlier observational period, 1950 to 1986. Their finding, storms resembling Éowyn, now show pressure anomalies up to 4 hectopascals deeper over Northern Ireland in the present period than in the past. Temperature anomalies are up to 5 degrees Celsius warmer in Scandinavia compared to the earlier period. Wind speeds in these storms are now up to 8 kilometers per hour higher over Scotland, Ireland, and the English Channel than they were in the historical baseline. And precipitation is up to 6 millimeters per day greater over Northern Ireland, Scotland, France, and Norway. These are not projections. These are measurements of what the storms are doing now compared to what they were doing before the atmospheric conditions changed. The storms resembling Éowyn, the ones that enter the same pressure field, track through the same region, draw on the same baroclinic zone, are measurably more intense now than their historical counterparts were. Faranda's team also applied the IPCC AR6 framing to their analysis. The IPCC's Chapter 11 on weather and climate extremes described limited evidence of observed changes in European extratropical cyclone behavior. Careful, cautious language that reflects the genuine difficulty of detecting signals in a noisy system with a relatively short instrumental record. But the Climameter attribution analysis offers a more targeted lens. Not whether all extratropical cyclones are changing, but whether this specific type of event, the deep, rapidly intensifying cyclone affecting the British Isle, is changing. The answer, in their analysis, is yes. 4 HPA deeper, 8 kilometers per hour faster, more precipitation. These are the fingerprints of a changed baseline. And here's what this means for the investigation we've been building. The Arctic paradox, a warming Arctic producing more violent mid-latitude winter weather, is not a theoretical prediction. It is observable in 7 decades of cyclone tracking data. It is quantifiable in the attribution analysis of specific recent events. And it connects directly to the infrastructure failure story we traced in Part 4. Because the power grid planning assumptions, the cold weather reliability standards, the emergency response frameworks, all of these were calibrated against a historical baseline that the observable data says has already shifted. And the shift is not small. There is one more dimension of the Arctic to bomb cyclone connection that the peer-reviewed literature has begun to document, and it runs in both directions. The Polar Amplification Model Intercomparison Project, PAMIP, a coordinated multi-model research effort, published in findings through 2026, identified that Arctic sea ice loss produces equatorward shifts of the jet stream and storm track in the North Atlantic. Equatorward shifts. The storm tracks are moving. The baroclinic zones where bomb cyclones form most frequently are shifting position as the atmospheric circulation responds to Arctic warming. This is not a marginal effect. It is a structural reorganization of where the most violent winter storms form, and therefore of which populations are most directly in their path. Planning frameworks calibrated against the historical storm track distribution are, under this finding, already misaligned with the current distribution, and the misalignment will grow as Arctic warming continues. The Arctic is warming. That statement has been in scientific and public discourse long enough that it may have lost some of its force. So let's be specific about what it means in the context of this investigation. The Arctic is warming approximately 2 to 3 times faster than the global average, not slightly faster, 2 to 3 times. That asymmetric warming, polar amplification, in the technical literature is not a future projection. It is an observable measurement. It is in the reanalysis data sets that go back to the mid-20th century, and it is producing a consequence that is, on first encounter, deeply counterintuitive. A warming Arctic is making winter more violent at mid-latitudes. To understand why, you need to understand what drives the polar jet stream. The jet stream is a narrow band of fast-moving air in the upper troposphere, roughly 6 to 9 miles above the surface, that meanders around the hemisphere in a roughly west to east direction. Its speed, the speed of the winds within it, which can exceed 200 miles per hour in its core, is powered by the temperature difference between the Arctic air mass and the warmer mid-latitude air mass to the south. A large temperature difference means a strong temperature gradient. A strong temperature gradient through the physics of thermal wind balance means faster jet stream winds. A fast jet stream tends to stay relatively circular, keeping cold Arctic air penned up in the polar region where it belongs. Here is the paradox. As the Arctic warms 2 to 3 times faster than the mid-latitudes, the temperature difference between Arctic air and mid-latitude air decreases. A smaller temperature difference means a weaker temperature gradient. A weaker gradient means a slower, more meandering jet stream, one that develops larger waves in its path, waves that can amplify into deep troughs and ridges that persist for days or weeks. A jet stream with deep, persistent waves allows cold Arctic air to push farther southward, sometimes dramatically farther, and warm mid-latitude air to surge farther northward. The cold outbreaks that result are more extreme than they would be in a world where the jet stream was stronger and more circular. Graham Madge, a spokesperson for the UK Met Office, described the mechanism in direct terms. When it gets to our level, it can cause disruption to the flow of the jet stream. The jet stream in a normal state is what drives our weather, and it is these interruptions to the jet stream which bring us different weather patterns. And Jason Furtado, a meteorologist at the University of Oklahoma, made the specific connection to bomb cyclones explicit. When the circulation around the polar vortex becomes less and less circular in shape, the cold air normally confined to the Arctic can expand southward to the mid-latitudes, including the US, Europe, and East Asia. This southward expansion of Arctic air doesn't just produce cold outbreaks. When that Arctic air collides with the warmer air over the Gulf Stream or the warm ocean surfaces along the east coast, the temperature contrast, the baroclinicity that drives explosive cyclogenesis, becomes sharper than it would otherwise be. The Arctic amplification mechanism is, in effect, loading the collision zones with more energy. It is simultaneously making the cold air colder and more available at mid-latitudes and making the ocean surfaces warmer. The two ends of the baroclinic contrast are both being amplified by the same global warming signal through different mechanisms, with the result that the conditions for explosive cyclogenesis are more intense than they were when Frederick Sanders was first describing the phenomenon. The peer-reviewed evidence for this intensification now spans decades of observational data. A study published in Communications, Earth and Environment, a Nature journal, in October of 2023 analyzed multiple reanalysis datasets covering the period from the 1950s through the 21st century. Its conclusion? The results indicate an intensification of Arctic cyclone activity over the last 7 decades. There has been a long-term shift of the maximum cyclone counts from weaker to stronger cyclones, and a pronounced lengthening of the duration of strong cyclones. The mechanism driving this intensification in the analysis was enhanced lower troposphere baroclinicity, amplified winter jet stream waves over the subpolar North Atlantic. That is the observational record, not a model projection, not a worst-case scenario. The last 7 decades of data showing a shift in the distribution of cyclone intensity, fewer weak events, more strong ones, and the strong ones lasting longer. The Climameter research team, led by David Faranda at the Institut Pierre-Simon Laplace in France, performed a specific attribution analysis of Storm Éowyn. They compared current era storms, 1987 to 2023, with equivalent storms from the earlier observational period, 1950 to 1986. Their finding, storms resembling Éowyn now show pressure anomalies up to 4 hectopascals deeper over Northern Ireland in the present period than in the past. Temperature anomalies are up to 5 degrees Celsius warmer in Scandinavia compared to the earlier period. Wind speeds in these storms are now up to 8 kilometers per hour higher over Scotland, Ireland, and the English Channel than they were in the historical baseline, and precipitation is up to 6 millimeters per day greater over Northern Ireland, Scotland, France, and Norway. These are not projections. These are measurements of what the storms are doing now compared to what they were doing before the atmospheric conditions changed. The storms resembling Éowyn, the ones that enter the same pressure field, track through the same region, draw on the same baroclinic zone, are measurably more intense now than their historical counterparts were. Faranda's team also applied the IPCC AR6 framing to their analysis. The IPCC's Chapter 11 on weather and climate extremes described limited evidence of observed changes in European extratropical cyclone behavior. Careful, cautious language that reflects the genuine difficulty of detecting signals in a noisy system with a relatively short instrumental record. But the Climameter attribution analysis offers a more targeted lens, not whether all extratropical cyclones are changing, but whether this specific type of event, the deep, rapidly intensifying cyclone affecting the British Isles, is changing. The answer, in their analysis, is yes. 4 HPA deeper, 8 kilometers per hour faster, more precipitation. These are the fingerprints of a changed baseline. And here is what this means for the investigation we've been building. The Arctic paradox, a warming Arctic producing more violent mid-latitude winter weather, is not a theoretical prediction. It is observable in 7 decades of cyclone tracking data. It is quantifiable in the attribution analysis of specific recent events. And it connects directly to the infrastructure failure story we traced in Part 4. Because the power grid planning assumptions, the cold weather reliability standards, the emergency response frameworks, all of these were calibrated against a historical baseline that the observable data says has already shifted. And the shift is not small. There is one more dimension of the Arctic to bomb cyclone connection that the peer-reviewed literature has begun to document, and it runs in both directions. The Polar Amplification Model Intercomparison Project, PAMIP, a coordinated multi-model research effort published in findings through 2026, identified that Arctic sea ice loss produces equatorward shifts of the jet stream and storm track in the North Atlantic. Equatorward shifts. The storm tracks are moving. The baroclinic zones where bomb cyclones form most frequently are shifting position as the atmospheric circulation responds to Arctic warming. This is not a marginal effect. It is a structural reorganization of where the most violent winter storms form, and therefore of which populations are most directly in their path. Planning frameworks calibrated against the historical storm track distribution are, under this finding, already misaligned with the current distribution, and the misalignment will grow as Arctic warming continues. The recommendation was not implemented. The same failure mode, infrastructure calibrated to historical baselines that a cold weather event exceeded, produced catastrophic outcomes in February 2021 and again in December 2022. Two different grid operators, two different regulatory frameworks, the same underlying dynamic, planning assumptions derived from past events that the atmosphere had already exceeded. March 12th, 1993. A low-pressure system is forming in the Gulf of Mexico. The conditions around it are unusual. A short wave trough in the northern branch of the jet stream has merged with the southern stream, fusing two atmospheric features into a single organized system with the pressure drop characteristics of a bomb cyclone and the geographic reach of nothing in living memory. The National Weather Service's lead forecaster on the event, Louis Uccellini, who would later become the NWS director, recalls the forecast process with the particular clarity that comes from watching something unprecedented in real time. So in that middle part of the week, we did start highlighting the potential for a major storm on the East Coast by the weekend. And when we got to day 3, we were putting a big storm on the East Coast on the maps, not pulling any punches. It was the first time the National Weather Service had accurately predicted the severity of a major storm 5 days in advance. That capability, the 5-day major storm forecast, was a milestone in atmospheric science. It saved lives. It allowed governors to declare states of emergency before the first snowflake fell. And it revealed, by the absence of that capability in all prior events, how many previous storms had killed people who didn't know they were coming. The 1993 storm of the century achieved a minimum central pressure of 960 millibars, comparable to a strong tropical storm, and affected approximately 40% of the United States population. Blizzard conditions from Alabama to Maine, hurricane-force winds along the entire eastern seaboard, 90 miles per hour recorded at Myrtle Beach, South Carolina, 101 miles per hour on Flat Top Mountain in the Appalachians. Temperatures of negative 12 degrees Fahrenheit in Burlington, Vermont. 56 inches of snow at Mount LeConte, Tennessee. 50 inches at Mount Mitchell, North Carolina. 43 inches in Syracuse, New York in 24 hours, an all-time record. 11 tornadoes touched down in Florida. And during the height of the storm, snowfall rates of 2 to 3 inches per hour across the mid-Atlantic and southern Appalachians. The storm killed 318 people in total, $5.5 billion in damage in 1993 dollars. 2.5 million people lost power. About 18,000 homes were damaged or destroyed. The Coast Guard rescued more than 160 people at sea. At least one freighter sank. But the number that has haunted the disaster response literature for 3 decades is not from the snow or the cold or the winds. It's from Florida. On the morning of March 13th, the storm's surge reached the Gulf Coast of Florida before adequate warning had reached the coastal population. Taylor County, in the Florida Panhandle along Appalachia Bay, was hit by a 12-foot storm surge. 12 feet, higher than many hurricane surges. And the people in the path of it had no storm surge, warning in any formal sense, because the warning systems for that kind of surge, the kind generated by an intense extratropical cyclone moving over a continental shelf at speed, did not exist in the form they exist today. 7 people died in the Taylor County storm surge. More people drowned in that single storm than had drowned combined during Hurricanes Hugo and Andrew. The National Centers for Environmental Information, in its documentation of the event, described the storm surge as arriving with little advance warning of incoming severe conditions. Some coastal residents were awakened in the early morning by the Gulf of Mexico rushing into their homes. And here is the institutional detail that connects 1993 to the present investigation. NOAA's National Hurricane Center now operates a formal storm surge watch and warning system for the Gulf and Atlantic coasts. It was established operationally in 2017. It was developed over years of consultation with social scientists, emergency managers, and broadcast meteorologists. It uses the slosh model, sea, lake, and overland surge from hurricanes, to predict where water will go and how high it will rise. But it only applies to tropical cyclones, to hurricanes, to tropical storms, to subtropical cyclones, and post-tropical remnants. When the NHC was asked whether the storm surge watch and warning system would ever be extended to winter storms. To the extratropical cyclones that produced a 12-foot surge in Florida in 1993, the agency's answer, as published in its current FAQ, is not for the foreseeable future. The system will only be issued for life-threatening storm surge events associated with potential and ongoing tropical cyclones. This is a structural gap in the warning architecture. A bomb cyclone that makes landfall at a coastline, driving a storm surge in front of it, does not trigger the most powerful storm surge warning tools in the NHC's operational toolkit. It triggers a coastal flood watch or warning, a weaker, more general product that does not carry the same urgency, the same visual design, or the same mandatory evacuation triggers. A winter hurricane can drive a surge that matches or exceeds what a tropical hurricane would produce, and the warning system treats it as a different, lesser category of threat. The 1993 storm of the century was not just a historic weather event. It was the first full documentation of what a compound winter weather event actually looks like when it kills people. Simultaneous blizzard, wind, cold, and surge, each one overwhelming a different part of the response system, the combination producing a death toll that is greater than the sum of what any single element would have caused alone. That architecture, simultaneous hazards, overwhelming systems designed for sequential ones, is the architecture of every major bomb cyclone event since. And it is the architecture that the systems protecting people from these storms were not, in 2022 or 2025, designed to fully address. The scale of the 1993 storm system is worth expressing in terms beyond deaths and dollars. The National Weather Service's Office of Hydrology estimated the storm's equivalent total water volume at 44 million acre-feet. That is comparable to 40 days of flow on the Mississippi River at New Orleans. It's enough water to flood the entire state of Missouri to a depth of 1 foot. This was not an unusual amount of precipitation for a large winter storm system. It is the total water transported and deposited by a single extratropical cyclone moving through a densely populated region. The storm's snowfall covered an area of more than 550,000 square miles and affected an estimated 120 million people. At the height of the event, snowfall rates of 2 to 3 inches per hour were occurring simultaneously across the Appalachians, the Mid-Atlantic, and New England. What the 1993 event confirmed, and what Elliott and Éowyn have since reconfirmed, is that the most dangerous aspect of a compound bomb cyclone is not any single element of its output. It is the simultaneity. Response systems organized around sequential hazard management, the blizzard teams, the surge teams, the power restoration teams operate on the assumption that they can address each problem in sequence. A compound event removes that assumption. The blizzard is happening at the same time as the surge, at the same time as the power failure, at the same time as the temperature extreme. The resources available to address any one of them are reduced by the competing demands of all the others. And the people who are most vulnerable to the combination, those who are elderly, those who have medical needs, those who lack transportation or adequate shelter, face simultaneous risk from every element at once. There is a phenomenon that occurs inside the most intense phase of a bomb cyclone that most people have never heard of, that virtually no casual weather coverage mentions, and that tells you something precise and important about the specific moment when conditions are most dangerous. It's called thundersnow. The name sounds almost whimsical. It doesn't prepare you for what it actually means. Thundersnow is a thunderstorm with lightning, with thunder, with convective instability reaching into the lower atmosphere, in which snow, rather than rain, is the primary precipitation. It requires the same fundamental ingredient as any thunderstorm: a column of air that is unstable enough to produce vigorous upward motion, strong enough to separate electrical charge in ice particles and drive lightning. But in thundersnow, that instability is compressed into the cold sector of a major extratropical cyclone, where temperatures are below freezing throughout most of the troposphere. Thundersnow storms are shockingly rare. Fewer than 7 out of every 100,000 thunderstorm events in the observational record involve snow as the primary precipitation. In the Northern Hemisphere, there are fewer than 10 synoptic scale thundersnow events per year on average. March is the peak month of occurrence, the period when the contrast between lingering Arctic air aloft and destabilizing surface temperatures creates the right conditions most frequently. It's not a phenomenon most meteorologists personally encounter more than a handful of times in a career. The locations where thundersnow is most likely are precisely the locations where bomb cyclones are also most likely. The Great Lakes region and similar environments where cold air interacts with relatively warm open water, and the comma head of a mature extratropical cyclone. Specifically, the northwest quadrant of the storm, beneath a trough of warm air aloft that produces the upper-level frontogenesis and strong vertical motion required for convective development in a cold environment. When thundersnow is occurring, snowfall rates of 2 to 3 inches per hour are typical. That is the rate at which cleared roads become impassable again, before the plow can complete a single pass. That is the rate at which visibility collapses to near zero within minutes of opening a door to go outside. That is the rate at which a car that stops moving, for any reason, can be buried to its windows within an hour. And here's the detail that distinguishes thundersnow from a summer thunderstorm in a way that makes it harder to track and harder to warn about: the thunder. In a summer thunderstorm, thunder is audible at distances of 10 miles or more. The sound carries easily through warm, humid air. In thundersnow, the snowflakes absorb and scatter the sound wave with remarkable efficiency. Thunder in a thundersnow event is typically audible only within 2 to 3 miles of the strike. A thundersnow cell can be directly overhead, producing lightning and convective snowfall rates of 2 to 3 inches per hour, and be essentially inaudible to a person 4 miles away. This acoustic compression means that the geographic signature of thundersnow in observational records is systematically smaller than the actual phenomenon. The number of thundersnow events in historical databases is an undercount because events that didn't have a weather station or observer within 2 to 3 miles went unrecorded. The rare events that are documented may represent a fraction of the actual frequency. The meteorological literature identifies the most common structural location for thundersnow within a major extratropical cyclone as beneath a trowel, a trough of warm air aloft. This is an inverted trough that extends backward from the main cyclone center into the cold sector, marking a region of upper-level frontogenesis and strong vertical motion where the convective development that drives thundersnow is most likely to occur. During a bomb cyclone at peak intensity, the trowel region can extend for hundreds of miles in the comma head, the same curved band of cloud and precipitation that carries the heaviest snowfall. This is not a narrow strip. It is the primary precipitation engine of the storm system. Thundersnow, in this context, is not occurring in a small anomalous corner of the event. It is occurring in the heart of the most productive snowfall region at the moment of peak storm intensity, in a swath of atmosphere that may be several hundred miles wide and that is moving across populated areas at speeds of 30 to 40 miles per hour. During Winter Storm Elliott, thundersnow was reported in the Buffalo area and across portions of the Great Lakes region, a signal that the storm had entered its most convectively active phase. The reports came in the hours when conditions were already being described as unsurvivable without shelter. Wind chills at -40, visibility at 0, roads impassable, and overhead, the rare combination of convective instability and below freezing temperatures producing lightning in a blizzard, muffled by the snow to a range of 2 or 3 miles. The storm at its most violent and its most silent simultaneously. What thundersnow tells a meteorologist looking at the data in real time is not a forecast detail. It's a diagnostic signal. When thundersnow is reported in association with a bomb cyclone, it marks the peak convective intensity phase of the event. The hours when snowfall rates are highest, when winds are most severe, and when conditions on the ground are least compatible with any form of movement. It is the storm showing its ceiling. And during Elliott's most intense hours in Buffalo, the hours when 37.5 consecutive hours of blizzard conditions accumulated their most devastating toll. Thundersnow was present overhead, muffled, overlooked, and marking the worst of it. There's one more physical dimension of this storm phase that demands attention, because the same convective instability that produces thundersnow is also in a bomb cyclone environment producing the highest snowfall rates at which the standard emergency response stack simply cannot keep pace. You cannot plow fast enough. You cannot treat roads fast enough. You cannot deploy enough personnel fast enough to stay ahead of 2 to 3 inches of snowfall per hour across an urban area in hurricane-force winds. The thundersnow phase is the phase when the emergency response system goes from stressed to overwhelmed. And what happens when it crosses that threshold is documented in the specific events of December the 24th, 2022, in Buffalo, in ways that the official record has been unusually candid about. The mathematics of snowfall accumulation at thundersnow rates are worth stating explicitly. At 2 inches per hour, the low end of convective snowfall rates, a road cleared at midnight is impassable again by 3 in the morning, even with continuous plowing. At 3 inches per hour, it is impassable within an hour of clearing if wind is redistributing the snow into drifts. Emergency response vehicles carry finite fuel. They operate on routes that assume a functional road network. When the road network stops functioning, not because the roads weren't plowed, but because the rate of accumulation exceeds any plowing capacity, the entire spatial logic of the emergency response system collapses. The vehicles are in the wrong places. The dispatch routing assumes roads that no longer exist. The personnel who would respond are themselves stranded. Thundersnow, in a bomb cyclone context, is not a dramatic weather phenomenon. It is the specific signature of the conditions under which a city's emergency response capability transitions from degraded to non-functional. At the height of Winter Storm Elliott's assault on Buffalo on December the 24th, almost every fire truck in the city was stranded. That is not a metaphor or an approximation. It is a statement by the governor of New York. Kathy Hochul reported publicly that almost every fire truck in Buffalo had become immobilized in the snow, not trapped at their stations. Many had responded to calls and were then unable to move through streets where drifting was filling the gaps faster than any vehicle could navigate. An emergency response capability that exists to protect a population of approximately 260,000 people was, for the critical hours of the storm's peak, effectively non-functional. 3 people died in Buffalo as a direct result of delayed EMS response due to impassable roads. These deaths are documented and attributed in the official record, not to the blizzard conditions themselves, not to exposure or hypothermia in the open, but to the failure of emergency medical services to reach patients because the roads through which those services travel did not exist in any navigable form. The people who needed help were in buildings. They were sheltered. They were in the places the emergency preparedness guidance tells people to be during a blizzard, and the system that should have reached them could not. The driving ban in Buffalo was in place for 5.5 days. The airport was closed for 5 days. Erie County Executive Mark Poloncarz described the scale of the response challenge in press conference after press conference, accounting for the dead in categories that reveal the compound nature of the disaster. Those found in vehicles, which the drifting had buried after the vehicle stopped moving. Those found outside in the elements, those who suffered cardiac events while shoveling, the physical exertion in sub-zero temperatures overtaxing cardiovascular systems under conditions where EMS could not respond, and those who died of carbon monoxide poisoning in one documented case from an improperly ventilated generator being run inside a building to replace lost electricity. The Oak Ridge National Laboratory's analysis of the grid and emergency response failures during Elliott was titled, with the careful understatement of federal research documents, Winter Storm Elliott, Energy Emergency Alert Lessons Learned. Its key finding was worth reading slowly. This report details how a predicted event, such as Winter Storm Elliott, can affect the U.S. power grid in unexpected ways, creating unanticipated challenges for power management organizations and utility companies. A predicted event. This was not a storm that arrived without warning, the National Weather Service had declared it a once-in-a-generation event and issued its most extensive warning coverage in recorded history. The system knew it was coming, and it still produced 45,000 megawatts of lost generation capacity, rolling blackouts in Tennessee and stranded fire trucks in Buffalo. The Tennessee Valley Authority's first ever invocation of the Electric Load Curtailment Program unfolded as a cascade of escalating requests. The initial Step 50 request from TVA, ordering local power companies to reduce load by 5%, came in rapid succession with additional steps and additional calls. The ORNL report described how the quick succession of steps and extra calls and texts created coordination challenges that the communication systems were not designed to handle at that tempo. The organizations that were supposed to coordinate with each other under an emergency had communication protocols designed for sequential emergencies, not simultaneous ones occurring across multiple dimensions of the same event at the same time. This is the compound event cascade in specific terms. It is not that each individual system, the grid, the roads, the emergency services, the communication networks, failed independently. It is that each system depends on the others in ways that are not visible until the simultaneous stress is applied. The grid goes down, which means heating systems fail, which means the population is in greater physical danger, which means the demand on emergency services increases, which is precisely the moment when emergency services are least capable of responding because the roads are impassable and the communications infrastructure is degraded. The grid repair crews can't reach the damaged infrastructure because the roads are closed. The roads can't be cleared faster than the snow is falling. The snow is falling at thunder snow rates, 2 to 3 inches per hour in hurricane force wind. Every intervention depends on a precondition that the same storm is simultaneously destroying. The ORNL report framed it as a lesson about communication systems. The FERC-NERC investigation framed it as a lesson about cold weather reliability standards. Both are correct at the level of their respective jurisdictions. But the deeper lesson, the one that neither investigation fully named, is that the planning framework for extreme winter weather events was built around a model of sequential hazards, each handled by a specialized response system. Blizzard, road crews. Power outage, utility repair, medical emergency, EMS. Each system optimized for its specific domain, none of them designed for the scenario in which all three domains are simultaneously overwhelmed by a single compound event that is moving faster and with more intensity than the planning assumptions anticipated. The reform process that followed Elliott, the FART cold weather standard proposals, the NERC reliability updates, the TVA after-action reviews, is a genuine institutional effort to close the gaps that the storm revealed. It is not nothing, but those reforms are calibrated against Elliott's parameters, the storm that already happened, measured in megawatts lost, and temperatures recorded and deaths attributed. What the climameter data and the 7-decade intensification record are saying is that Elliott's parameters are not the ceiling. They are a data point in an escalating distribution, and the next storm may not give the planning process the time it is taking to update. The carbon monoxide death during Elliott is worth naming specifically because it illustrates a failure mode that compound events reliably produce and that preparedness messaging rarely addresses adequately. When the power grid fails in a major cold weather event, a portion of the affected population turns to backup generators, portable, gasoline-powered generators that produce electricity but also produce carbon monoxide as a combustion byproduct. Those generators must be operated outdoors or in a well-ventilated space to be safe. In a blizzard, running a generator outdoors means placing it in conditions where it can be buried in snow, blocked by drifting, or rendered inaccessible. The alternative, operating it in a garage, a basement, or an enclosed porch, produces carbon monoxide that accumulates to lethal concentrations within minutes. Every major winter storm that combines power outages with extreme cold produces carbon monoxide deaths among people who are following the intuitive logic of keeping the generator close to the building in dangerous outdoor conditions. It is a documented, predictable consequence of the compound event. The preparedness messaging for most power outage scenarios does not adequately convey the lethality of this specific combination. The deaths keep occurring. The pattern is not mysterious, it is structural. At this point in the investigation, 3 threads are running simultaneously, and it is worth naming them clearly before we look at the forward projection data. The first thread is the atmospheric one. Bomb cyclones form through baroclinic instability, the collision between cold and warm air, and are intensified by latent heat release from warm ocean surfaces. The Arctic is warming at 2 to 3 times the global average, destabilizing the polar vortex and increasing the frequency and severity of cold air outbreaks at mid-latitudes. The North Atlantic sea surface temperatures have been at or near record levels since 2023. The upper atmospheric conditions that support explosive cyclogenesis, the jet stream positioning, the upper level divergence, the baroclinic zone sharpness are all being modified in ways that favor more intense events. The second thread is the observational one. The 7-decade data record, analyzed in the Communications Earth and Environment study published in October 2023, shows a measurable shift in Arctic cyclone intensity. Fewer weak events, more strong events, and stronger events lasting longer. The climameter attribution analysis of Éowyn shows that storms of that type are now measurably 4 hectopascals deeper and up to 8 kilometers per hour faster than their historical counterparts. These are not model projections. They are measurements of what is already happening. The third thread is the infrastructure one. The planning framework, protecting the grid, the emergency services, and the population depends on historical baselines that the observational data says have shifted. The Louisville cold weather standard was 49 degrees below the temperature the atmosphere actually produced. The grid reserve margin was more than 3 times NERCA's minimum target, and still failed to prevent rolling blackouts. The storm surge warning system explicitly excludes the category of storm that produced a 12-foot surge in Florida in 1993. Now let's look at the forward projection. David Ferranda and the climameter team's analysis of Éowyn establishes that storms resembling it are now 4 HPA deeper in present-day conditions than in the 1950 to 1986 baseline period. Haley Fowler at Newcastle University, watching that data, is direct about the implication. As the climate gets warmer, we can expect these storms to become even more intense with greater damages. That statement is not a prediction about a hypothetical future. It is an extrapolation of an observable trend stated by a professor of climate change impacts at a research university about events that are already in the observational record. Climate Central, which tracks global sea surface temperature data daily, reported that North Atlantic temperatures remained at near record levels through 2025, following record-breaking conditions in both 2023 and 2024. Warmer ocean surfaces mean more moisture available for evaporation. More moisture means more latent heat released during condensation in a developing storm. More latent heat means faster deepening rates during explosive cyclogenesis. The fuel is warmer than it has ever been in the instrumental record. The compound dimension matters here too. Robert Fritzen's 2021 study established that approximately 7% of all non-tropical low-pressure systems near North America from 1979 to 2019 were bomb cyclones, an average of about 18 per year. The same study established that 69% of Pacific bomb cyclones occurred between December and early March. That seasonal concentration means that the peak frequency of these events overlaps with the peak vulnerability of energy infrastructure. The period when heating demand is highest, when cold weather stresses generation equipment, and when the consequences of grid failure are most acute. If the storms at the high end of the intensity distribution are intensifying faster than the mean, if Éowyn represents not an outlier, but a direction of travel, then the recurrence interval for an event of that magnitude is shortening. The 1945 Irish wind record stood for 80 years before Éowyn erased it. The question that follows from the climameter data is not whether future storms will match Éowyn. The question is whether 80 years is still the right time frame to think about for the next record-breaking event. The Communications Earth and Environment study identified the mechanism, driving the 7-decade intensification trend as enhanced lower troposphere baroclinicity and amplified winter jet stream waves over the subpolar North Atlantic. Those are the precise conditions that the Arctic amplification mechanism is expected to reinforce. The feedback is not circular in the mathematical sense, it is not runaway, but it is consistent. The mechanism driving more intense bomb cyclones is the same mechanism that the observational data shows is already producing more intense Arctic cyclones. The connection is not speculative. It is in the peer-reviewed literature and in the measurements. There's one more number worth sitting with before we move into the assessment section. In 2022, the Louisville cold weather standard was 49 degrees below the atmosphere's observed output. That 49-degree gap is not the gap between the standard and a model projection. It is the gap between the standard and what had already happened in that city, in that winter, in that storm. The atmosphere had already exceeded the planning assumption by 49 degrees in a winter that the planning framework considered a once-in-a-generation event. If the climameter data is correct, if these events are 4 HPA deeper and 8 kilometers per hour faster now than they were in the 1950 to 1986 baseline, then once in a generation is not the right recurrence interval. It is the recurrence interval for the last generation storms. The seasonal concentration of bomb cyclones, 69% occurring between December and early March, means that the risk is not distributed evenly across the calendar. It is concentrated into the 12 to 14 weeks when energy infrastructure is under its highest heating demand stress, when cold weather stresses fuel supply chains, and when the consequences of grid failure are most acute for the most vulnerable members of any population. Elderly people in inadequately heated buildings, patients on home medical equipment that requires electricity, families in low-income housing with thin walls and no backup heat source. The population that suffers most from a bomb cyclone grid failure is not evenly distributed across income levels or housing types. It is concentrated among the people who have the fewest resources to self-rescue from a prolonged cold and power emergency. The planning frameworks that are being updated in the wake of Elliott and Éowyn are making decisions about acceptable risk levels that will be borne disproportionately by these populations. That is not a political statement. It is a demographic fact embedded in the data from every major winter weather disaster in the modern record. Before we reach the assessment section of this investigation, there's something that needs to be addressed directly. Because the topics covered in this series, extreme weather events, institutional preparedness gaps, escalating atmospheric violence, attract a specific category of alternate explanation that circulates online with considerable energy. And I want to be honest and specific about those explanations, because dismissing them with contempt doesn't serve the audience, and neither does leaving them unaddressed. The most common alternate explanation for events like Éowyn and Elliott involves HAARP, the High Frequency Active Auroral Research Program, the research facility in Gacona, Alaska, operated by the University of Alaska Fairbanks and jointly funded by the Air Force, the Navy, and DARPA. HAARP has been the center of weather modification claims since its construction in the 1990s. The claims take different forms: that it is used to direct storms, steer jet streams, weaponize precipitation, but the underlying assertion is the same: that a technological system operated by the U.S. government is capable of generating and directing the kind of atmospheric violence that this investigation has been describing. I want to address this directly because it deserves an honest answer grounded in physics, not just dismissal. HAARP's maximum radiated power output is approximately 3.6 megawatts. That is an electrical specification measured at the antenna. It represents the total energy the facility is capable of transmitting into the upper atmosphere at its highest operational setting. 3.6 megawatts is a substantial amount of electrical power for a research transmitter. It is approximately the output of a small industrial generator. Now consider the energy budget of Storm Éowyn. A mature extratropical cyclone at peak intensity carries kinetic energy on the order of 10 to the 21st joules. That is 10 followed by 21 zeros. To put that in comprehensible terms, the energy in a single major extratropical cyclone is comparable to the total energy released by hundreds of thousands of nuclear weapons of the Hiroshima scale. The rate at which a bomb cyclone at peak intensity is dissipating and reorganizing energy vastly exceeds the total output of every power plant currently operating in the United States, running simultaneously. The gap between HAARP's 3.6 megawatts and the energy budget of a single mature bomb cyclone is approximately 14 orders of magnitude. That means HAARP's maximum output is roughly 100 trillion times too small to meaningfully interact with the energy dynamics of the storm system it is claimed to control. This is not a matter of classified technology. It is not a question of whether HAARP has hidden capabilities. It is a question of physics. There is no mechanism by which 3.6 megawatts of radio frequency energy transmitted into the ionosphere can alter the heat fluxes, pressure gradients, and baroclinic instabilities that drive a storm system carrying 10 to the 21st joules of energy. The scales are not comparable. They are not even in the same category. The desire to explain extreme weather as a product of human agency, as something being done deliberately rather than being caused by accumulated diffuse, decades-long human activity, is understandable. It imposes narrative structure on what would otherwise be an enormous, slow-moving, systemic problem without a clear antagonist. But the actual human fingerprint on these storms is both more mundane and more alarming than any directed energy system. It is greenhouse gas emissions, accumulated since the Industrial Revolution, raising global temperatures, warming ocean surfaces, melting Arctic sea ice, accelerating polar amplification, destabilizing the polar vortex, and loading the baroclinic zones where bomb cyclones form with more energy than they carried 50 years ago. That fingerprint is not a claim. It is in the measurements. It is in the climameter data showing Éowyn-type storms now 4 HPA deeper than their historical counterparts. It is in the 7-decade intensification trend in Arctic cyclone activity. It is in the record North Atlantic sea surface temperatures that provided the latent heat that allowed Éowyn to drop 50 millibars in 24 hours. It is in the Louisville 49-degree gap between the cold weather planning standard and the temperature the atmosphere actually produced. The real story doesn't need the conspiracy. The ordinary physics is alarming enough, and it comes with 45 years of observational data, named scientists, and peer-reviewed literature to back it up. One more fringe claim worth addressing before we move to the assessment: the idea that official warnings are deliberately understated to prevent public panic. The Elliott case is the most direct rebuttal. The National Weather Service issued the most extensive warning coverage in the agency's recorded history. NERC's winter assessment had warned about the risk of supply shortfalls. The Weather Channel predicted Elliott would become a bomb cyclone 2 days before it did. The warnings were not understated. The failures were failures of planning assumption, of infrastructure that was not calibrated to the atmospheric conditions that arrived, not failures of information suppression. The institutions warned. The physics exceeded what the infrastructure was designed to handle. Those are two different problems, and conflating them with a conspiracy narrative obscures the second one, which is the one worth fixing. There is also a methodological point worth making about the climameter attribution analysis that this investigation has cited. Attribution science, the discipline of determining how much a specific weather event was intensified or made more likely by climate change, is a relatively young field with genuine methodological debates. The climameter team's comparison of current era and historical era storms is a specific analytical approach with specific assumptions. It is not the only approach. Other studies, including those that informed the IPCC AR6 assessment, reached different conclusions about the detectability of changes in European extratropical cyclone behavior. The IPCC's position of limited evidence is a legitimate scientific judgment, not an institutional cover-up. The honest position is that the climameter findings are one signal in an active scientific conversation, a signal that is physically coherent, methodologically defensible, and worth taking seriously, but not settled consensus. The investigation has presented it as that, a significant finding from a named research team, with the IPCC's more cautious framing also on the table. Both deserve to be in the picture. The fringe explanation that someone is controlling the atmosphere requires neither. It is not even wrong in the scientific sense. It is simply physically impossible. We've covered a lot of specific evidence in this investigation. Pressure drops, megawatt losses, temperature gaps, wind records, storm surge warnings that don't apply to winter storms, emergency services that couldn't move, a grid reserve margin that evaporated in 48 hours. All of that evidence points toward a central question. Is the gap between what these storms can do and what the systems protecting people are designed to handle getting better or worse? That question has three honest answers, and I want to present all three of them because the data supports different readings and because the intellectual honesty of presenting competing interpretations is the only way to keep this investigation credible. Let me be specific about what each one actually claims and what evidence supports it. The first interpretation is the most generous to the institutions, and it deserves a fair hearing. The systems are working, and they're being updated. After Elliott, FERC, and NERC launched a formal joint investigation. Cold weather reliability standards were proposed. The TVA conducted a thorough review and committed to corrective actions. After Éowyn, the EU civil protection mechanism was activated, and Ireland received emergency generators from Poland and Denmark. Engineering crews from Austria, Finland, France, Great Britain, Germany, the Netherlands, and Norway. 7 nations deploying resources to restore power to a country hit by a storm that its grid infrastructure couldn't fully absorb. That's a functioning mutual aid framework operating under extraordinary stress. The 5-day weather prediction capability that Louis Uccellini credited as a milestone in 1993 is now standard. The NWS issued comprehensive warnings before Elliott. People who heeded those warnings and stayed off the roads were not among the dead. The warning systems are better than they were. The grid investigation process is active. The climameter attribution science is advancing. The institutions are responding. Under this interpretation, the gap is real but closing. The planning frameworks are updating in the direction of more accurate baselines, and the pace of reform is approximately proportional to the pace of change in the threat. Éowyn's mutual aid response, 7 nations and 30 days of restoration work, is evidence that the systems can absorb even unprecedented events and recover. The deaths during Elliott and the outages during Éowyn are the cost of a transition that is underway, not a fixed condition. The second interpretation is the one I find most supported by the totality of the evidence, and I want to be clear that it is not a pessimistic reading. It is a precise one. The planning frameworks are updating, but they are updating for past events rather than projected future conditions. The cold weather standard proposed for Louisville after Elliott was derived from historical records, from what the coldest temperatures had been in that location in the decades before the analysis was performed. It was updated from the old baseline to a slightly less old baseline. But Arshad Mansour's admission, our planning process does not take that into account, referring to the effects of climate change on extreme weather, was made after the investigation, not resolved by it. The climameter finding that storms resembling Éowyn are now 4 HPA deeper and 8 kilometers per hour, faster than their historical counterparts, is a measurement of the present. It is not built into the proposed reliability standards that follow from the Elliott investigation. The FEAR cold weather standard proposals were calibrated against what has already happened in the PJM service area, against the historical record of extreme cold extended to capture Elliott. They were not calibrated against the projection that Arctic amplification and warming ocean surfaces will continue to intensify the high end of the distribution. Gordon Van Wheely's question, who is responsible for mitigating the impact of these risks, was asked in September 2022. It was still unanswered when Elliott arrived 3 months later. The FERC-NERC investigation was still being processed when Éowyn arrived 13 months after that. The regulatory and infrastructure update cycle operates on a timescale of years. The atmospheric escalation documented in the 7-decade intensification record operates on a timescale of decades. The question is whether the update cycle is fast enough to close the gap, or whether the gap is widening faster than the institutions can act. Under this interpretation, the gap is not closing. It is holding approximately steady or widening slowly. While the threat moves away from the historical baseline, the planning frameworks are still being calibrated against. The deaths and failures in Elliott were not a planning failure in the sense of inadequate warning. They were a planning failure in the sense of infrastructure and response capacity calibrated for a storm that has since become, in the observational record, a below-average representative of its type. The third interpretation is the most concerning, and I present it because the evidence supports it as a possibility that deserves honest consideration rather than reflexive dismissal. The planning and response framework contains structural assumptions that cannot be updated by incremental reform because they are embedded in infrastructure investment timelines, regulatory jurisdictions, and political incentive structures that operate on decadal timescales. The 49-degree gap between Louisville's proposed cold weather standard and the observed temperature during Elliott is not an error of analysis. It is a consequence of a regulatory process that must find politically defensible numbers grounded in historical records, amenable to cost-benefit analysis, acceptable to the utilities and ratepayers who will fund compliance. The result of that process is, by design, a backward-looking standard that captures past extremes and adds a margin. It cannot capture the forward projection because the forward projection is contested, because infrastructure investment decisions made on the basis of a contested projection carry political risk, and because the institutional incentive structure rewards minimizing near-term costs over mitigating long-term risk. The storm surge warning gap. The explicit policy decision that the NHC's formal storm surge warning products will not, for the foreseeable future, apply to winter storms, is not the product of ignorance about winter storm surges. The 1993 event is thoroughly documented in the institutional record. It is a resource allocation and jurisdictional decision. Extending the storm surge warning system to extratropical events requires retraining, retooling, model updates, and coordination with the NWS offices that handle winter weather, all competing for resources in an agency that operates under the same budget pressures as any federal institution. Under this interpretation, the gap is structural rather than incidental. It is not primarily a problem of insufficient information or insufficient will. It is a problem of systems, regulatory systems, infrastructure investment systems, emergency response systems that were designed for a more stable atmospheric baseline and are not capable of adapting at the pace the observational data suggests is necessary. The deaths in Buffalo, the lost megawatts in PJM, the 8-decade records falling in Ireland. Under this interpretation, these are not aberrations that reform will prevent from recurring. They are the leading edge of a recurring pattern. Only the data that accumulates over the next several storm seasons and the institutional decisions made or deferred in response to it will determine which of these three interpretations is correct. But there is one thing the data already confirms without ambiguity, and it's worth stating plainly. Strip away the interpretations, strip away the policy questions and the regulatory debates and the three-option framework. What does the evidence in this investigation actually confirm? It confirms that explosive cyclogenesis is a physically real and well-understood phenomenon, producing hurricane-force winds, blizzard conditions, coastal storm surges, and catastrophic cold simultaneously in mid-latitude regions that were not designed for tropical-scale wind events. It confirms that the threshold for classification as a bomb cyclone, 24 millibars in 24 hours, is, in the most intense recent events, a floor rather than a ceiling. Storm Éowyn dropped 50 millibars in 24 hours. Elliott dropped 35. Both exceeded the threshold significantly. The threshold describes a minimum, not a typical. It confirms that the observational record, spanning 7 decades, shows a measurable intensification of Arctic cyclone activity. Fewer weak events, more strong events lasting longer. This is not a projection. It is a measurement, The Communications, Earth and Environment study published in October 2023 established it from multiple independent reanalysis datasets. The mechanism, enhanced lower troposphere baroclinicity and amplified winter jet stream waves, is consistent with the effects of Arctic amplification that are independently observable in the temperature record. It confirms that the climometer attribution analysis of Storm Éowyn found that storms of its type are now measurably 4 HPA deeper and up to 8 kilometers per hour faster than equivalent storms in the pre-warming baseline period. That is a present tense measurement of a present tense change in storm intensity. Haley Fowler at Newcastle University drew the only reasonable conclusion from that data. Storms are already more intense, and they will become more intense as warming continues. It confirms that the infrastructure protecting people from these events was built against historical baselines that the observational record shows have shifted. The Louisville cold weather standard was 49 degrees below the temperature the atmosphere produced. The PJM grid reserve margin was more than 3 times NERC's minimum target when 45,000 megawatts failed. The storm surge warning system has a documented exclusion for the type of event that drowned more people in 1993 than Hurricanes Hugo and Andrew combined. It confirms that the compound nature of these events, simultaneous wind, blizzard, cold, and surge, each overwhelming a different domain of the response system, is not a new discovery. It has been documented in every major bomb cyclone event from 1993 through 2025. The response systems are still organized around sequential hazard management rather than simultaneous compound event management. That architecture was present before Elliott. It was present after Elliott. The ORNL and FERC-NERC investigations analyzed it. The architecture has not fundamentally changed. What is genuinely uncertain, and what the evidence does not confirm, is the rate of change. The 7-decade intensification trend in Arctic cyclone activity is a statistical signal in a noisy system. The climometer analysis of Éowyn is a measurement of storms resembling that specific event. It does not constrain the full distribution of extratropical cyclone behavior. The IPCC AR6 position of limited evidence for observed changes in European extratropical cyclone behavior is a calibrated assessment of a scientific community that correctly insists on statistical rigor. The honest position is that the signal is visible, the mechanism is physically coherent, and the rate of change remains an open quantitative question. What is also uncertain is the return period for events of Éowyn's magnitude. The 80-year Irish wind record is a data point. One data point does not establish a new return period. If the climometer finding is accurate, if Éowyn-type storms are now genuinely and persistently 4 HPA deeper and 8 kilometers per hour faster, then the recurrence interval for Éowyn level intensity is shorter than the historical record implies. But by how much is a question the current data cannot resolve with precision. And what is unknown, not merely uncertain, but genuinely open, is what a simultaneous polar vortex displacement event and North Atlantic bomb cyclone would look like arriving over a major American metro area in the same 48-hour window. The polar vortex literature identifies bomb cyclones as possible precursors to stratospheric polar vortex disruption. The disruption, in turn, can send cold Arctic air southward for weeks to months following the triggering event. The scenario in which a bomb cyclone triggers a polar vortex displacement that extends its cold air outbreak significantly beyond the storm's own duration is not hypothetical. It is documented in the scientific literature as a physically plausible mechanism. Its full implications for infrastructure that was calibrated against shorter, cold events have not been fully analyzed in any public planning document this investigation identified. Frederick Sanders coined the word bomb in 1980 because he wanted to convey destructive potential and sudden change. The word has traveled a long way from the monthly weather review since then. It has passed through news alerts and school closings and social media graphics and 1,000 weather broadcasts. It has become, in many ways, a word that people file away under bad storm and move on. That filing system is the gap. Not the gap in the grid, not the gap in the warning architecture, the gap between what the word now means in the observational record, in the attribution science, in the 7-decade intensification trend, and what it sounds like to most people who hear it. There is one confirmed thread in the data that deserves its own moment before we close this section. Not a projection, not an attribution finding. A confirmed observational pattern that the planning literature has largely failed to formally address. Bomb cyclones are documented precursors to stratospheric polar vortex disruptions. The polar vortex, the large-scale circulation of cold air in the upper atmosphere that normally keeps Arctic air contained at high latitudes, can be disrupted when sufficiently strong wave energy propagates from the troposphere into the stratosphere. That wave energy can be provided in part by intense extratropical cyclones. The disruption, once it occurs, can send sudden stratospheric warming events cascading down through the atmospheric column over days to weeks, weakening the surface vortex and producing prolonged cold air outbreaks that strain infrastructure for weeks rather than days. The research literature, including Attard and Lang in 2019 and Pangs in 2019, identifies bomb cyclones as among the possible precursors for this mechanism. What this means in practical terms: a major bomb cyclone is not necessarily a self-contained event with a defined beginning and end. Under the right upper atmospheric conditions, it can be the triggering event for a weeks-long cold air outbreak that arrives after the storm itself has moved on. The storm knocks out the grid for 48 hours. The polar vortex disruption it helped trigger keeps temperatures 30 degrees below normal for 3 more weeks. The infrastructure calibrated against the storm duration was not calibrated against the aftermath. This scenario has not appeared in any public grid planning document this investigation identified as a formally analyzed scenario. It is in the scientific literature. It is not yet in the planning framework. There's a reason this investigation started with a name, with Frederick Saunders and John Giacomo in 1980 choosing a word carefully. Naming something is the first act of attention. It says, this phenomenon is real. It has measurable properties. It matters enough to mark in the record. The data we've covered in this investigation is the accumulation of attention paid by a specific community of people: meteorologists, atmospheric scientists, grid engineers, disaster researchers, to a phenomenon that most of the population experiences, when they experience it at all, as a severe inconvenience rather than a systemic signal. Saunders and Giacomo paid attention in 1980. Robert Fritzen paid attention across 40 years of North American storm data. Davide Ferranda and the Climameter team paid attention to the difference between what Éowyn did and what its historical counterparts did. Louis Uccellini paid attention to what the models were showing 5 days out in 1993 and refused to pull his punches. Mark Poloncarz stood at a press conference and accounted for every death, one category at a time, because that is what accountability looks like when the system fails. What we know from the data, bomb cyclones are intensifying. The Arctic is warming in ways that are amplifying the baroclinic zones where these storms form. The ocean surfaces providing their fuel are warmer than at any point in the instrumental record. The storms are already 4 HPA deeper and 8 kilometers per hour faster in the attribution analysis than their historical counterparts. The infrastructure protecting people from them was calibrated against a historical baseline that has shifted. What we know from the institutional record: the warning systems performed in Elliott. The warnings were issued. The storms were described accurately in their broad parameters. The failures were failures of infrastructure calibration and compound event planning, not failures of meteorological science. Those two things are different, and conflating them leads to the wrong reforms. What we don't know: how fast the distribution is shifting, what the return period for Éowyn level intensity now is, what a simultaneous polar vortex disruption and major North Atlantic bomb cyclone arrival would look like over infrastructure that wasn't designed for that combination. What the grid failure mode looks like when the cold weather gap is 60 degrees instead of 49. Signal Watch is going to stay on this. The coming storm seasons carry data that will either confirm or complicate the climameter attribution findings. The FERC Cold Weather Standard implementation process will produce public documents that can be compared against the atmospheric projections. The post-Éowyn grid analysis from Ireland and the UK will add European data to what has, in the American context, been a discussion about one side of the North Atlantic. We are going to keep watching, and we are going to keep telling you what the data actually says, not what the official communication frames it as saying, and not what the fringe alternatives claim it means, just what the instruments measured. What the scientists found, what the record shows. There are specific things to watch for in the coming seasons. The FERC Cold Weather Standard implementation process will produce public dockets, regulatory filings in which grid operators will argue for or against specific temperature thresholds. Those thresholds can be compared directly against the climameter projection for what the atmospheric baseline now supports. That comparison will tell us something real about whether the institutional update cycle is closing the gap or widening it. The post-Éowyn grid resilience analysis in Ireland and the UK will produce European data on how a 700,000 customer outage from a single storm is being absorbed into infrastructure planning. Data that the American conversation about grid resilience has largely proceeded without. And the coming North Atlantic storm seasons will either confirm or complicate the 7-decade intensification trend. Each major event is a data point. The distribution either continues shifting toward more intense storms at the high end, or it doesn't. The record will show which. Frederick Sanders was a careful man. He chose the word bomb, not for drama, but for precision, because precision was what the situation required. The situations keep arriving with that word attached. The precision it was chosen to convey has not diminished. What has changed is the frequency with which the atmosphere is validating it, and the gap between the scale of what the word describes and the scale of what the systems meant to respond to it were built to absorb. The investigation continues. You've been here for this one. The community that makes this possible is not an abstract. It is the people who watch these episodes to completion, who share them with someone who would want to know, who leave comments that tell us where in the world this is landing and what questions it's raising. You are why we can do this work at the depth and length it deserves. If you found this investigation valuable, please share it with one person who should see it. Not as a viral action, as a deliberate one. One person who you think would want to understand this. That is how this community does its best work. Person by person, story by story, with attention paid to things that matter. The stories that matter take time. We're grateful you give us yours. We will be here when the next one arrives, and we will be watching.